Okay, Math 9. Back at it again with lesson 3.2, the exponent laws. And the way I like to introduce this topic is that by the time you're done, you'll learn to do things with these things we call exponents. We're going to be able to do a lot of arithmetic with them. Add them, subtract them, multiply them, and we'll learn what anything to the zero power equals. Now there's a lot more to exponents, but this is just the start. So simple arithmetic with exponents, and we'll get going right about now. Multiplying powers. Let's scroll that one down. When we look at something like 2 to the fourth times 2 to the fourth, this means essentially you've got the same base, the base is 2 and the power is 4, but you're multiplying this times itself. Let's write that in full. This is like 2 times 2 times 2 times 2, and let's represent this with a really big multiply. 2 times 2 times 2 times 2. Okay, so there's our 2 to the fourth, and there's our 2 to the fourth. Now, if the exponent law is simply about figuring out how many times the base is being multiplied, you can see that we've got 1, 2, 3, 4, 5, 6, 7, 8 2's being multiplied. Move this over a little bit. 2 to the power of 8. Two to the 8th power. So 2 is being multiplied by itself 8 times. Take a look at those 4's, and you might have seen the pattern already. Imagine what you do with those. We'll move on. We'll see if this pattern emerges. In the example below, we have -4 times -4, I'll draw that with parentheses, multiplied by -4 multiplied by -4. Stop and ask yourself, how many times did the -4 get multiplied by itself? 1, 2, 3, and there you go. There's the fourth multiplication. So we're starting to see a pattern emerge with multiplying when we're talking about the same thing. The above example, the base was 2. The example in this case, the base is -4. So we could say that -4 was multiplied 4 times. Alrighty. Next example is interesting in a couple of respects. You have to look at these 6's and say how many 6's are being multiplied. Same idea. 6 times 6, okay, that accounts for this, multiplied by a lonely little 6. Well, there's just one of them, right? Just one 6 here. So the understood exponent is 1. There's just one of them there. The only thing you can't put to the first exponent, okay, is a 0. And I'll explain why later. For now, in this example, we can see that we've got 6 to the third power. And I think our example would like us to scribble it here. 6 to the third power. You'll find really quick that as you're doing these, you could be writing the multiplications over and over and over again, or there may just be a simpler way. I'll show you that simpler way now. What if I told you that the base, well, as long as the base is the same thing, in this case a 9, that instead of writing this, and running out of steam after a while because that's a lot of writing, what if I told you that you could write the base 9 and that you could just add the exponents? Let's just undo that there. I'll just choose a different color then. It's going to be a pain. Let's choose a nice, I don't know, a nice burnt orange. That you could just simply add the exponents as long as the base is the same thing. 9 to the 6th power. Now, again, notice that we're multiplying, So when we're multiplying, how many times is the base being multiplied? 1, 2, 3, 4, 5, and 6. So it must be okay to say that this is the same as 9 the base to the third power, and the rule is you can just add the powers. That works with multiplying as long as the bases are the same. If we look at our examples above, and I'll just zoom out a little bit, each of these examples is showing this. We should write in 9 to the 6th power here. Undo. So just looking at this, when it says evaluate, I just wanted to clarify, it's asking, well, what does this equal? You can put this into your calculator and it'd take a little bit of work, and that's fair. In this case, I'm much more interested in expressing the number with its exponent. Two to the 4 plus 4. That's how we got this. Negative 4 to the 2 plus 2. That's how we got this. 6 to the 2 plus 1. That's how we got that. And our last example, 9 to the 3 plus 3, which is how we got this. Again, keep the exponent raised higher, and I use the Statue of Liberty example. Evaluate in our scribble notes here is asking you, well, what does it equal? It's perfectly fine to leave it in exponential notation. If it doesn't come to mind what 2 to the 8th is, you can just leave it as 2 to the 8th. I'm fine with that. Imagine if I asked you what is 10 to the 100th power, and I said, oh, okay, what does that equal? What does that evaluate to? That'd be a very huge number. But 10 to the 10th power, okay, that's a way of expressing the answer. It's absolutely factual, it's accurate. So by evaluation, what we'll leave it at for now, and I've been doing it, is we'll just leave the evaluations as these. There we go. Come here, highlighter. Awesome. Now you get a chance, take a look at these, pause the video for a moment and see if you can figure these out on your own. Now when you're done factoring these out, or determining the answer, more accurately stated, see if yours match mine. Remember when two things, for this question, when two things are side by side in parentheses, it means multiplication. So 1, 2, 3, 4, 5's here. 1, 2, 3, 4, 5, 6 of them here. Oops, and we have just enough room at the end. I just have to hit scroll. So your product, if you want to write it accurately, is just saying, well, they could have just said evaluate. What does this equal? 3 to the 6th power, 5 to the 10th power. And this last one's a little bit larger. I'm kind of tired of orange, so I'm going to choose a different color. Let's go with, I don't know, a dusty purple here. How many 8s do I have? 1, 2, 3, 4, 5, 6 there. And 1, 2, 3, 4, 5. 8 to the 6th power times 8 to the 5th power. Understand that you can only say that it's 8 to the 11th power because the base is 8. You couldn't do this with 8s and 7s. It would be a very different story. 8 to the 6 plus 5. And if you count each one, there's 11 8s being multiplied, or 8 to the 11th power. Sorry, I have to pop back up here. So we've discovered a rule, and that rule is that when you multiply powers with the same base, then you simply add the powers. Just moving up here. Oh, I have to hit undo. I hate it when it does that. We'll write the first part of our rule, which would be that a base, let's say it's a base to some value. So it's a formula. So a to the m multiplied by a to the n is simply an addition of their exponents. A just represents any number. It could be 2, 3, 5. Voila. There we go. So our first rule is in place when we're multiplying values that have a similar base. We're multiplying 2s, 3s, 8s, what have you. Now, what happens if we have dividing? Now, if you think about this logically, multiplying two values with a similar base, you add their exponents. So you think for a second, you say, oh, if you added their exponents, what would you do when you divide? Oh, you'd probably subtract their exponents. If that's your logical guess, you're not far off. And it's a pretty quick thing to show. Take 4 3s, and by division, what I'll do is I'll put a dividing line and divide those 4 3s by 2 3s on the bottom. Okay, how many of these 3s cancel out? Now, if you're good at your canceling, if you're not, pay attention. There's a 3 here and a 3 here. Those cancel. That's like dividing 3 by 3, and they each become 1. So I'll just I'll cross them out. This 3 and this 3, they cancel out, and I'm left with these final 2. I'm just left with 2 3s. 3 times 3. And a better way of saying that is 3 squared. Now, based on our prediction, what we could have said is if they have the same base, we could have taken 3, we could have taken the first exponent as it appears, this 4, and subtracted 2, and gotten 3 squared, or 3 times 3, and it turns out that prediction is accurate. So dividing similar bases, you can subtract the exponents. At this point, don't worry, we'll try to make sure you don't get negative exponents, but yes, they can happen. This is a parenthetical, so it's shining the spotlight on the -5 and saying the base is -5. There's no doubt about it. -5, so here's my prediction, -5, and I'll subtract the exponents. Now I'm guessing that what I would have is -5 to the first power. So if you have a lonely -5 and it's all alone, you can just say, well, this is just a -5. Okay. If you had this, you could see pretty quick these 5s will cancel out and these -5s will cancel out, and that you're left with just this sole solitary -5. There's just one of them left. Your final answer? -5. There you go. You could say -5 to the first power, but it's just a -5. This final example is quite interesting because if you do the fractional example, 8 times 8 over 8 times 8, well, think about that for a second. That's kind of like 64 divided by 64, isn't it? Well, that cancels out and equals 1. these go equal into each other one time. All you're left with is a full cancel. And by canceling, you say 8 divided by 8 is 1, and 8 divided by 8 is 1. So a rule has popped up here, and I don't know if you realized it, but it proves a mathematical rule that anything to the 0 power equals 1. Now there's an exception to this. Okay, pay attention to that. Little rule, anything to the 0th power equals 1. There's an exception to this because 0 is an absence of value. You can't have 0 to the first power equaling 1. 0 is an exception. 0 to the first power does not equal 1. It simply equals 0. So we don't work with 0. We work with numbers other than 0. So in evaluating this, I am more than happy to say that this is 3 squared, this is -5, and if you really feel obliged to the first power, and that this is 8 to the 0, which equals 1. I'm happy with that. We've discovered a law, which is when you divide bases that are the same, in this case 3's, these are -5's, and these are 8's, if the bases are the same and you're dividing, really because of the canceling, you can subtract the exponents. That's the whole reason. In our example below, I'll simply cross out the 5's that would cancel. You would be left with just 5 times 5, or 5 squared. In this example, there's 4 8's there. Say goodbye. See you later, 4 8's. And we'll kill 4 of the 8's here. So this is explained by saying 5 to the 4 minus 2 equals 5 squared. And this is 8 to the 4th power, or rather, undo, hoo-hoo, that's the bottom. The top is 8 to the 7th power, and that 7th power is being subtracted by the 4 8's on the bottom, and you are left with 8 to the 3rd power, and there's our 3 8's as we saw. What's left, sort of last man standing type stuff, is 8 to the 3rd power. Back up to the top and say, okay, what rule have we learned? That when multiplying things that have the same base, you can add their exponents, but when you're dividing things that have the same base, you can subtract. Okay? Absolutely. Zoom in, as I sort of need to make space. So any number, so as long as the bases are the same, a to the subtract the first from the second exponent. There we go. Okay, second rule is in place. Nice to know these mathematical rules. And quite honestly, once you learn this, you'll never forget it. These notes are important though, because if you do forget, scribble it in. When dividing powers with the, again, it's understood, and if it isn't, you make the point that the base has to be the same. In each of these examples, the base was exactly the same before you did any work. If not, these rules don't apply. Subtract. Let's make that a little bit better. Okay, rule number 2 in place. Power of a power. So we've done subtracting and adding of exponents. What about multiplying them? What is required to multiply them? Interesting example comes up right here. Let's zoom in on it. What if we have some number which has already got an exponent raised to another power? Let's sort of say, well, that's kind of interesting. What do you mean? Well, let's take something other than a green color, because I think I need to go back to purple. What if we had 2 cubed, right, to the third power? And what if that happened twice? What does that mean? That's 2 times 2 times 2 multiplied by itself twice. Well, that's like 2 to the 6th power. How in the world could I have gotten the 6th power without having to write out all this schmutz? There's a way. Look at that 3 and look at that 2. It's a power of a power. And I tell my students, if there's a neat parenthetical separation like this, if there's that good old curve there, you can multiply the exponents. 3 times 2, 6. And that's what they're trying to indicate to you. You can multiply the exponents. It's like exponent arithmetic, but you have to know the rules. Of course, below we develop a couple of these examples further so you don't miss it. And we can show it longhand. 3 times 3 times 3 times 3 times 3 times 3. Okay, we get the idea. 1, 2, 3, 4, 5, 6 multiplications. If you'd like to do it a little more simply, you could do 3 to the 2 times 6. Notice that I show it as a... Now, it's technically called, when you raise text up like that, the 2 and the 6, sure, it's the powers. Sometimes you'll hear it called a superscript, but in math, we generally tend to call it a power. That evaluates out to 3. Oh, did I say 3 to the 2 times 6? Whoa! Let's go back. Oops. Undo. I was making a point and I ran away with myself here. 3 to the 2 times 3. There we go. Got ahead of myself. 3 to the 2 times 3, which is 3 to the 6th power. Oh, that happens sometimes. This is, of course, is getting a little tedious, but 2 times 2 times 2. And that whole, this is called 2 cubed, is done twice. Okay, now we can see that it's 2 cubed, and if that's done twice, you technically could say 2 cubed squared. Sound would kind of weird, but it just means that we have 2 to the 6th power. And because we have a way of verifying that, like this, which you see below, right here, we know that our figuring is correct. We refer to this as power of a power. So 2 to the 3rd, and the of part is the multiplying. Let's pop up to the top. We've observed a rule here, and whenever you observe a rule, you want to write it down. So, sorry, I'm trying to make you dizzy. Ooh, right here. And let's go with a different color. We'll go with brown. If some number, a, is to some power, let's call it m, and that is raised to another power, then the base a has its exponents multiplied. Boom. There we go. Done. Another rule we could sneak in here that we haven't highlighted yet, but we really should, we'll go with blue, is that any number raised to the 0 power equals 1, but a cannot be equal, so that's what this means, is not allowed to be equal to the number 0. And by 0, you can put a 0, or another way some people write 0 sometimes is like this, so that you should never use the letter O to represent a number, because O looks so much like 0, sort of bad form in mathematics. So our rules have popped out pretty darn well. We've got the mathematical rule, we've got the division rule, so let's check these off. There's the multiplication rule, product, we've got the division rule, we've got power of a power, and we just have a few more to go. So let's pop on down and see if we can get this finished. These rules in general are pretty well all the rules you'll need. Okay, raising a product to an exponent. So section D. Zoom in because we'll need to. This is an interesting example because you need to write in the understood exponents. So each of these, there's just 1, 2 being multiplied by a negative 3. And that's kind of interesting because we've got two numbers inside. Roughly what we're saying is we've got, let's just erase that, undo. We've got this portion here, and we've got a power out here, and we've got this portion here, and again, there's the power outside. Oh, redo. I need those ones. Let's make those ones a little more obvious. Is there an easier way to do this? Well, the value inside could just be evaluated. You could do BEDMAS, and you could say, well, 2 multiplied by negative 3 is negative 6 to the 4th power. Now that's fair to say. Let's write that down. Negative 6 to the 4th power because of what you see here. Okay, keep that in mind. What if we take power of a power, just to what's inside? Could we say that we've got 2 to the 4th power times negative 3 to the 4th power? Now, if we work this out in full, 2 to the 4th power, 2 times 2 is 4, times 2 is 8, times 2 is 16. And 3 to the 4th power, I'll help you out with that, that's 81. Okay, that's pretty interesting. 6 to the 4th power. This is roughly like saying negative 6, not roughly, accurately. I have to wall these off from each other. There we go. Let's see what these equal. Are they the same? So if we did the work inside, is our answer the same as if we raised the bits inside? If we raised the 2 to the 4th power and the negative 3, let's see what happens if we did that. Do we get the same answer? So I have to pop out of my lesson for 1 sec. Sorry. I can't do split screen. 6 to the negative 6 to the 4th power. All right. Back this up a little bit. 6 negative. Oop, that didn't work. To the 4th power. Oop, oh, cursed here. Negative 6 to the clear. It's a slightly different calculator than I normally use. There we go. To the 4th power. There we go. 1296. Okay, thanks for bearing with me. The answer, let's put it in red, 1296. So if we did it that way, what is 16 times 81? Okay, I'm betting on 1296. Let's find out. Look at that, 1296. They're the same value. Back to our work. What this proved is that you can follow the Bedmans rules and multiply the factors inside and then take them to the exponent, or the factors inside can have their power of a power done and you will still get the same answer. Pretty slick. So this is called raising a product to an exponent. But the factors of the product can be raised to the exponent. You get the same answer. Very, very cool. So how do you write that? You go back up to your rules, and since it's raising a product to an exponent, there we go. Need a little bit more room. Okay. Raising a product to an exponent. Yeah, let's stick with red. So if we had, I'll use some different ones now, and I have to make a line. If we had some number, so let's use x, and x multiplied by y, let's say it's x to the power of, well, let's just use an example. We'll put these to the 1, just because that's convenient. And if we raise that to, let's use an example like this, 2, you could accurately write this as the first exponent times, and we'll write times this way, and you've got the second base, which is y, and that could be written, need a little bit more room, I'll just borrow this. There you go. It's really just power of a power for different bases. If you think about it that way, that's exactly what you're observing here. If the bases inside are different, if two values are being multiplied, a 2, a 3, a 4, and a 5, and they've got exponents, keep an eye on the power outside. Let's go down a little bit further here. Okay. So raising, here you go, raising a product to an exponent. Let's get out our rules, get a color we can stand. When a product is raised to an exponent, you can apply the exponent, well, let's just say the power of a power rule, to each base. And you see that right there. And it totally works out. Okay. So what happens if you get something like a fraction? Now, don't let it throw you. A fraction, sometimes you would say a fraction's answer is a quotient. Like 1 divided by 2 is 0.5. What if you had a fraction raised to an exponent? Right? You have the top and the bottom, the numerator, the denominator. What do? Well, you have to treat the top and the bottom the same, right? We'll come down to this example C right here. 2/3 to the 5th. Okay, so let's go the long route. Is like 2/3 times 2/3 times 2/3 times 2/3, and you get the idea. Well, there's 5 2's on the top, 5 3's on the bottom. Well, I see power of a power right here. And I see it right there as well. If we wanted to back up and make this a lot simpler, we could have saved ourselves all sorts of headaches. So I'll hit the magic undo button. And we could have just said, using it's just power of a power, what we're doing, 2 to the 1 times 5 over 3 to the 1 times 5, which evaluates to our final answer, 2 to the 5th over 3 to the 5th. Again, realize they're different bases. Treat the numerator and treat the denominator as if they're just bases and you're just applying power of a power. We've gone and more or less done the work for this whole question. That's what you should see in here. And the final answer, 2 to the 5th over 3 to the 5th, is what you can just write over here. 2 to the 5th over 3 to the 5th. It's not bad. Going back to, just back up a little bit, do the first example. Repeated multiplication. In this case, let's highlight that exponent. So we have 3 times 3 multiplied by -4 times -4. That's what this is saying. Another way of writing that, of course, 2 3's, 2 -4's, 9 times 16. So this is power of a power. Just understand, it's 3 to the 1st, and it's -4 to the 1st. And once you see that, you see if it's power of a power rule, that you could have just written it like this at the end, just by multiplying their exponents. Because 1 times 2 is 2, and 1 times 2 is 2. So their powers make sense. There we go. Probably fill in this last quick example. 4 to the, zoom in. Again, you got to put in those understood exponents, right? 4 to the 1st times 6 to the 1st. Well, you could do these power of a powers right here, meaning that your answer is, hate it when it does that, meaning that what you have is 2 4's being multiplied and 2 6's being multiplied. That's what this says. But once you see that it's power of a power, you should just say 4 squared times 6 squared. And it comes out to the exact same thing. F, we've kind of already seen, we've proved. With the exception of 0, anything to the power of 0 equals 1. Be careful when you're looking at your base again. If the base isn't 0, When the exponent of a power is 0, the value of the power, it just means the answer, is 1. There you go. Make that a little tidier. Coming up on the assignment down here, one last thing I need you to do. Is negative 8 squared the same as highlighted negative 8 squared? This goes back to our example from our previous lesson. And I'm going to write Bedmus here to clue you in. Because exponents are more important, higher priority, than multiplication. This is one of those what I like to call the sneaky examples, simply because this is 8 squared, this is the negative of 8 squared. 8 squared is 64. You have to do that first. Taking the negative of means multiplication. The exponent had to be done first. So if you do that, you say 8 squared is 64, and then you apply the negative. That is very different, because in the second example, we've got negative 8 times negative 8. These units, these negative signs, rather not units, but these negative signs, cancel out, and you're left with 64. It's a positive value. Now that's different. We don't have a minus sign hanging around out in front of the 8. Because this is in parentheses, that's the base. It's negative 8 squared. The previous example, the base was positive 8 squared, and then you just took the negative of the answer. Negative 64 does not equal positive 64. On a number line, those are 128 jumps apart. Be very, very careful. If you see, let's change colors for one more quick second. Come back here, you. Let's go to blue. If you ever see this, and you go to compare it to, let's push that off. These are totally different. The parentheses, in this case, tell you what the base is. There's no parentheses around this. So this is positive 3 squared, and then it's ruined and it's made negative. That's like multiplying the answer, which is 9, by negative 1, which gives it a negative 9. That is radically different than negative 3 times negative 3, which gives you a positive 9. Because when you compare them, they're totally different values. They're actually 18 values apart. Very important to note. That, ladies and gentlemen, has been an introduction to the exponent laws. Make sure we filled it all in here. There we go. And power of a quotient, I guess we got to fill that guy in. Little more room. So you'll have to forgive me. I will use, let's use a color that we've seen. And I'll just use a real example for this. So power of a quotient. So if you had x over y, and that was to, let's say, some power. Let's call it n. Let's make sure, let's say these are to the 1. That this is x, and I'll say 1 times n. Whatever x is exponent, this is just power of a power, over y's exponent with power of a power. So I'm just using a 1 as an example. And we're left with this result. So this is just a sneaky power of a power game right here. Okay, and then I'll just undo that so you can see it. Okay, folks, that has been power of a, well, that's been a lot of powers, let's put it this way. We like to call it the exponent laws. And we'll give you a shot, we'll give you an opportunity. We'll give you an opportunity to take these out for a spin now. All right, have a good one.